Hello everyone, and welcome back to the Kohi Game Engine series. Today we're going to talk about uniforms. I would like to take a quick second and thank the supporters of the channel, beginning with our partners, Eearslya, Wensheng, Caden, and Patrick. They are the partners of the channel, which is the highest tier of support for the channel, so thank you very much for that. And I would also like to thank all the other supporters listed here on the screen. Your support is very much appreciated, so thank you for that. If you're interested in supporting the channel, you can find links in the description to YouTube memberships, as well as my Patreon page, which is patreon.com/Travis Vroman. So, last time, we left off here, where we drew our first triangle and then our first quad on the screen. And we did this by uploading vertex data that contains positional information and some color information. And then we were able to use that in the shader to be able to interpolate these values, right? So it's great that we can upload per vertex information, but this doesn't necessarily cover everything that we're going to need to do. There is some information that is a little bit higher level than this that needs to be consistent across all vertices. These are things like ambient environment color, your camera transforms, so that would be your view matrix, your perspective matrix, and several other properties that we're going to be adding along the way. And so obviously that is not the type of data that you want to upload once per vertex, because not only would that be a hideous waste of space, but it would be highly inefficient. Enter what we call uniforms. Uniforms are essentially variables that we can use in our shader at a higher level that are consistent across basically the entire draw call. It's a little bit more complicated than that, but that's for the purposes of this explanation right now, let's just think of it that way. And so what we're going to do is we are going to add uniforms. However, with most things Vulkan, it's not quite as simple as just adding uniforms to our shader code and then adding a few lines of code and getting it to run. So first off, I'm going to start at the shader level. And we're going to take a look at our shader here, where we have our built-in object shader. And we're going to take a look at what we need to actually feed into the shader. And then from our application side, we'll go ahead and feed in that data. So the first thing that we're going to want to keep in mind is that we're going to have different levels of uniforms, right? There are going to be some uniforms that apply to the whole scene. That'll be like our camera matrix, for example. And there will also be uniforms that we'll want to have per object that we render. And that might be, let's say, a model matrix, right? The actual individual orientation of an object in space. And so at least initially, we're going to focus on the global uniform. And those uniforms are going to be like our projection, our view matrix, our ambient color, and a few other things. And so we're going to build that out first, just to sort of get an understanding of how all of this works. So the very first thing that we're going to do is in our built-in object shader.vert.glsl, we are going to come down here below our out position, and we are going to define a uniform. And this might look like a structure that you'd find in C, because it actually is very similar to one in this case. So we are going to be defining something called a global uniform object. This object is going to contain the various properties that we need. So right off the bat, we are going to be adding a projection and a view matrix to it. And those are both of type mat4, which matches our matrix 4 on the application side. So we have one for projection, one for view. Now, I should point out here that I am loading these all into a single uniform, which you can think of as a single variable. However, another way that you could do this is, if you wanted to, you could have them as separate uniforms and just do it this way, right? And so we could have one for projection, one for view, and so forth. And basically your binding would increase for each one that you add, right? So I'll come back to this set and binding for a second, but each one of these uniforms has a unique binding that indicates basically what quote-unquote slot that uniform fits into. And we have one per uniform. However, I am electing not to do this because it actually complicates things on the application side. And it makes things a little bit cleaner to just include it all as one. So I am going to be including it as a single uniform that is a structure that we're going to call global uniform object. Okay? And so to finish off this declaration, we are going to name that global UBO. Okay? And so this is the, you can think of this as the structure definition, and then this here is the name of the variable that we're going to be using. So anytime we refer to this, we are going to be referring to global UBO. Now, if you think back to our previous videos discussing what the projection matrix is, that's been gone over a couple of times so far in the series, so I'm not going to re-explain that here. The view matrix is simply a matrix that we use to represent the camera's orientation in space. So these are the first two things that we are going to be adding to our global uniform object. And this is going to allow us to sort of navigate the scene a little bit later on and move a camera around it. Okay? And so we will be adding properties to this as needed, but for now that is all we need to do in terms of adding the global UBO structure. Okay, so the next thing that we're doing in our shader here is we're just using the position, the in position that we're sending directly, right? And this is fine if we just want to blit directly to the screen. However, we don't actually want to be doing that here. We actually want the camera to affect how the geometry is drawn on the screen. And so what we'll actually need to do is some multiplication between these two, as well as something that we're later going to have, which is called a model matrix, that is the individual object's orientation in the world. And we'll multiply these three matrices with this value in order to get what we need. Now, you might ask why we are not including model here. And as I mentioned before, this is our global uniform object. And so by global, I mean this applies to the whole scene. So since the model is per object, it does not apply to the whole scene. We are not going to include it here. And in fact, I'm actually not going to include it at all just yet because we are actually going to use a different way of setting that, okay? So for now, we are just using projection and view. Okay. The other thing I'm going to do is, since this out position was sort of just a temporary thing to show how to pass between shaders, I'm actually going to remove it. We don't need it anymore, okay? And so now we're going to take our global UBO's projection and view matrices and apply it to our position here. So first we can remove this line here just to simplify things. And our GL position is now going to be made up of our global UBO, okay, dot projection times our global UBO dot view times the in position. Okay, and whenever we get ready to add the model matrix, incidentally, that will be added basically right here between these two, right? So you want to add, you want to multiply in this order. That's actually pretty important. You want projection, then view, then model, then your position. Okay, and so we'll come back to the model later, but right now we're just going to add projection and view. Okay. All right, so that concludes what we need to do in our object shader, right? So we're going to be making a structure like this that gets passed into our shader. However, since we remove some things that are getting passed to the fragment shader, we also need to update that. So in this case, we have our in position here. We're actually going to eliminate that because we don't need that anymore. And our out color, we're actually just going to go ahead and set back to white. Okay. And eventually we will be passing some additional information here to color this a little bit differently, but for now we're going to go ahead and leave that as is. Okay, and so that should handle those. So I'm actually going to go ahead and run a task, and I'm going to do post build, and we see that our shader is built successfully, so we're good to go there. Okay, so at least the shader side of things is done. That's the easy part. So next, we need to talk about our Vulkan object shader. So the way that we're structuring this application is our individual shaders are also going to be responsible for managing uniforms. And this is done because this is handled a little bit differently between Vulkan and OpenGL and DirectX, right? And so we want to abstract all that away and just sort of abstract it behind this sort of shader structure here. So this is where we're going to be adding that stuff. And we are going to add it in the form of descriptors. Now, you'll note here that I have this descriptors comment here as a to-do, and we are now actually going to be adding those things. So what is a descriptor? Well, up until now, we've been uploading just geometry through attributes. Our descriptors are actually what holds our uniforms. And descriptors are actually used for other stuff as well. We will be coming back to that, but one of the things that descriptors are actually used for is to hold uniforms. So we are going to be creating some descriptors to hold our global uniforms. And so the first thing that we're going to do is within our shader, we're going to set up some descriptors and then populate those. And we will populate them with a global uniform object. However, before we can do any of that, we actually need to define our global uniform object. So if we go to render types INL, we need to declare a new type here. So I'm going to type def a structure, and we're going to call this global uniform object. Okay, and this is going to hold all of our global data that we're going to use in our shaders sort of across the board. And note that I'm doing this in render types, not in Vulkan types, because this isn't a Vulkan specific thing, this part of it, right? The data that we're going to be populating here is going to be used no matter what kind of renderer backend we are going to be using, okay? And so the first thing that we need to do is we need to create a matrix for our projection, okay? And since we have our matrix 4 here, let's go ahead to be safe and go ahead and add a include to math types, okay? And so we have a matrix 4 for our projection and a matrix 4 for our view. Now, one thing that I want to point out that has run me into a little bit of an issue in the past with uniform buffer objects, which we'll get into that in a minute, what that means, is that they have to be a given size specifically for NVIDIA cards. And I know this is a little bit weird and we haven't really talked about memory alignment and whatnot, but NVIDIA has a requirement, or at least they do on some, in some cases, that uniform objects need to be 256 bytes in size. And so what we have here is we have 64 bytes here and we have 64 bytes here. And so what we actually need to do is we need to pad this out to make it 256 bytes. So I'm going to add a just an M reserved 0 here, and I would add a copy of that, and we'll call it M reserved 1. Okay, and what we'll do is as we add properties to this global uniform object, we will subtract that memory space from one of these things. And so that way it'll maintain that 256 byte size rather. Okay. And so again, I haven't gotten into memory alignment and some of those discussions yet. At some point we'll be covering that in greater detail, but for now, just sort of accept this as it is, that this global uniform object needs to be 256 bytes in size. And so we can achieve that with 4 matrix 4s. Okay, so the only ones we're actually going to use are these first 2 for now. Okay, so now that we've done that, now we need to actually head over to Vulkan types and take a look at our object shader, because there are a couple things that we need to add to our shader here that are sort of maintained by it as part of its state. And one of those things is the global uniform object. And I'm just going to call this global UBO. Okay, UBO, there we go. And so this is what is known as our global uniform buffer object. So we will be feeding this into a buffer, which is then tied to a descriptor, which then gets uploaded to the GPU. And we'll go into that whole process in a little bit, right? So I want to cover the data aspects of this first, and then we'll actually cover how it's loaded. All right, so we have our global UBO. The next thing that we need to set is we actually need to set up some stuff to be able to create our descriptors. However, as with a lot of other things in Vulkan, descriptors are not just easily created. Descriptors are actually allocated from a descriptor pool. And a descriptor pool is something that you set up to say, we have a maximum number of, say, 10 descriptors, for example. And anytime we allocate, we pull from that pool, and anytime that we throw away a descriptor, we put it back in that pool for something to then come and pick up at a later time. So we have a descriptor pool, we have a descriptor. However, we have something that is called a descriptor set. Now, a descriptor is basically, you can think of as an individual uniform. A descriptor set is a bundling of those uniforms, right? So if we have multiple uniforms, we can have multiple sets. So to put this into perspective, if we actually go back to our shader for a second, there is something that I alluded to before here. So in our definition here for our layout for our UBO, we have set equals 0. So this set equals 0, the set refers to a descriptor set. Okay, and so this is basically saying that we have a set of descriptors here, and this is the first descriptor within that first set. Okay, so if we go back here to Vulkan types, we need to create a couple of things here. So we need, first off, a descriptor pool, which I'm going to call for now a global descriptor pool, because that's pretty much what it is, right? It's for our global descriptor sets, right? And we'll also go ahead and create an array of 3 descriptor sets called global descriptor sets. And as you can see here, we have 1 descriptor set per frame, a max of 3 for triple buffering. And this again has to do with the same concepts that we've touched on in the past, where we can be rendering multiple frames at the same time, or be rendering one frame while another frame is being presented. And so we actually need to maintain separate descriptor sets for each one of those frames. So we have a maximum of 3 in case we're using triple buffering. If we're using double buffering, this would be 2. However, these are relatively small in size, so I'm just, to avoid dynamic allocation, I am just using 3 here, because worst case scenario, we just don't use one of them. So we have our descriptor sets. These are what are actually going to hold our bindings. And then we have our descriptor pool. However, there's one more piece to this that we need to do, and this is called a descriptor set layout. And the descriptor set layout defines what the layout of a descriptor set is, right? So the descriptor set layout is used by the descriptor pool when it goes ahead and creates. It knows how much memory to allocate, what the layout of those descriptors are, what data types they are, etc. And it knows how to handle that based on the layout, right? And so all 3 of these pieces are necessary in order to actually use descriptors, okay? So I hope all that makes sense. And one more thing I'm going to do is I'm actually going to take the pipeline and move it down here to the bottom. Great. One more thing that I mentioned before is you've heard me use the term uniform buffer object, okay? And so we have our uniform object here, right? But this is not our uniform buffer object. Oops. And I actually have buffer in there, and that's actually incorrect. this is just the global uniform object. So what is the uniform object buffer? Well, put simply, it is a buffer that holds the global uniform. And this is tied to a descriptor set. So we need a Vulkan buffer that is our global uniform buffer, okay? And there's actually only one of these, so let me get rid of that S. So this is where we load this data into, right? And then this Vulkan buffer here is attached to our descriptor set, which is then uploaded to the GPU. So you can kind of hopefully understand how all these pieces come together, okay? All right, so I believe that is actually all we need to do as far as data structures are concerned for right now. So let's go back to our Vulkan object shader, and we will go ahead and get rid of this to-do for descriptors because we're going to set that up now. All right, and I'm actually going to change this to global descriptors, okay? And so the first thing that we need to do is we need to define our descriptor set layout binding, okay? And so that looks something like this. So we create a VK descriptor set layout binding. We say here that our binding is 0, meaning it's the first one. How many descriptors we have one descriptor because we're passing one object. Again, if we were to go back to our shader here and have multiple of these uniforms, right? Like if we were to split this out, then that number would be 2. But we're doing this all as one object, so we have 1 here. The descriptor type is VK descriptor type uniform buffer, okay? And this tells it how this descriptor is actually going to be used. Now there is something, there are other types here that we can actually use, such as image samplers for textures, but for right now, this is all we're gonna need. And then our immutable samplers is set to 0, and then our stage flags for right now, we are only gonna be using this in the vertex stage bit. So we don't need to set the fragment stage because it's not actually used there. We're only using this in the vertex shader stage, right? So in the vertex shader. If we had a uniform that we wanted to use in the fragment shader, then we would go ahead and add that flag there as well. But we're not doing that, so we're only using vertex, okay? So next, we have our descriptor set create info, right? Which just basically takes our S type as we might expect. Says how many bindings do we have? This is our single binding right here. So you have one of these per binding. We only have one, so we use 1 here. And then we just pass the address of that binding to have that be treated as an array here for P bindings, okay? And that is our descriptor set layout. So now that we have this, as you might expect, we need to call VK create descriptor set layout. So this just takes the logical device, our global layout info, which we've created here, our allocator, and then the address of our global descriptor set layout. So this is what's actually going to fill that out, right? And of course we surround that whole thing here with a VK check. Let me get these out of the way so we have a little bit more space here. All right, so we have our descriptor set layout. The next thing we need to do is we need to set up our descriptor pools. So the first thing that we do is we create a descriptor pool size, right? And we're just going to call this global pool size. The type is uniform buffer, right? This should match what's up here. And then the descriptor count is, we're using the swap chain image count, okay? And we technically could just use, we could use a hard-coded 3 here, but whereas we have reserved the number of descriptor sets in this struct here to be 3, we don't necessarily need to do that here. So it's okay to just use the swap chain image count here. If you're more comfortable with it, you could just do this and it'll be fine, because this is really just the pool. So whatever you guys are comfortable with will work for that. I am using this. You don't have to use that if you don't want to. Okay. So the next thing is we need a create info for our descriptor pool. So this is just a global pool info with our S type here. Our pool size count is 1. That is not how many actual elements are going to be in the pool. It is just saying what the number of size objects we are passing is. So in that case, it's just 1. Okay. And our pool sizes is obviously an array, so we just pass the address of global pool size. And then here, the max sets is what actually says how many descriptor sets can be stored in this this particular pool, right? And again, we're going to be using image count. Okay. All right, and finally, as you may have guessed, we'll go ahead and do our global descriptor pool. In fact, I'm going to move this comment up here. Okay, and we create our descriptor pool, right? So we call vk create descriptor pool, logical device, the address of our global pool info, our allocator, and the out shader global descriptor pool, the address of that, right? And so now, of course, we wrap this whole thing in a vk check, and that is our descriptor pool created. Okay. All right. So if we recall, we also have a to-do here for descriptor set layouts. And this then gets plugged into these two, what we're passing 0 right here for the Vulkan graphics pipeline create, which is our descriptor set layout count and an actual array of those layouts, okay? And so we need to actually go ahead and fill those in. And I had put the to-do here, but I think I'm actually going to wind up moving this. No, I'm going to leave it there. So let's go ahead and get rid of this to-do. And this is our descriptor set layouts. So the first thing we're going to do is we are going to create a layout of vk descriptor set layouts. And for right now, this is going to be an array of 1 because we only have 1, okay? And we are going to set that to out shader global descriptor set layout, okay? And so it seems a little bit silly, I realize, to just create an array for just 1 entry, but we are going to be adding descriptor set layouts to this, remember. So we don't want to have to come back and change the structure. It makes much more sense to just build it this way for now. Okay. And so that is our layout. And the other thing that I'm going to do is I'm actually going to include a const i32 descriptor set layout count, and I'm going to set that to 1. Whoops, 1, not 11. Okay. And this will allow me to be able to change both of these things sort of in the same place, right? And so now here, I believe it's the count first and then the descriptor set layouts. So now I can just pass count here as the first 0 and layouts there, okay? And now our layouts will be passed into the pipeline and automatically added as we might expect. Great. So that is our descriptors created. However, there's one more piece to this, which, if you recall, we have the buffer that we actually need to set up. So we have here our pool has been created, our set layout's been created, our descriptor sets have been created. This we haven't filled out yet, but at least we've reserved it. So we need to actually create this guy here, which is the global uniform buffer. So that is going to be the next thing that we're going to do immediately after we create the pipeline. Okay, so if we get here, then we're going to go ahead and create the uniform buffer. And I'm just going to go ahead and paste this in and then describe it. Okay, so we call our Vulkan buffer create, which right now is actually not defined. So let me go up here to the top, and we need to actually include that. So we'll put that right underneath pipeline, okay? And we'll come back down here. And what we're looking at is we call our Vulkan buffer create, we pass the context, And then we pass the size of our global uniform object, right? And this is going to tell us how big that buffer should be. It's a really small buffer, but that's okay because it's a global one, right? So it kind of gives you an idea of how we're going to do this. Some of the usage flag bits, which is the next thing, is basically we're going to say that this is a transfer destination, as well as it's going to be used as a uniform buffer, right? So we're going to be able to transfer things to this, and then the GPU can use it as a uniform buffer. The other thing that I want to point out is the memory usage. So we have the memory device local, but it's also going to be host visible so that we can upload to it directly, and host coherent, okay? The next thing is bind on create, which we are going to be binding on create, and the out buffer is going to be set to the address of out shader global uniform buffer, okay? And if this fails for some reason, obviously we'll bleat about it and boot out. So that's our uniform buffer. Pretty straightforward to create at this point, thanks to the way that we've set this up. Okay, so we've set up our descriptor pools and our descriptor set layouts. However, we haven't actually allocated our global descriptor sets yet. So that is going to be the next thing that we need to do. And as you may recall, there are 3 of them. So what we're going to do is we are going to create an array of descriptor set layouts. And we're going to call this global layouts. It's going to be hard-coded to 3. And we're basically going to paste the same layout in here 3 times. And this is going to be used to allocate our 3 descriptor sets, okay? And it seems a little bit silly to have to do it this way, but technically these could all be different layouts. So you actually have to provide the layout per descriptor set, okay? And so the next thing is going to be a structure to say what we are going to be allocating, right? So it has an S type to say descriptor set allocate info. The descriptor pool is going to be the global descriptor pool on our out shader. The descriptor set count is going to be 3. And then the set layouts is going to be our array here, okay? And we'll go ahead and allocate that by calling vk allocate descriptor sets. We'll pass the logical device, the allocation info that we just set up, and the out shader global descriptor sets array. Okay, and that will go ahead and populate that. And that is all we need to do to stand this up to get it ready to use. So before we move on, we should probably come in here and make sure that we actually destroy things as necessary, right? Because if you try to destroy this shader without destroying all this stuff we just created, there are going to be problems with that. And so one thing I'm going to do is, just for convenience sake, I'm going to save off a pointer to the logical device. And the very first thing we're going to do is destroy the uniform buffer, right? We'll go ahead and we'll make sure to destroy the pipeline, since that was right here, okay? And then the next thing is we'll need to destroy, after that, the global descriptor pool, okay? And not only do we need to destroy that, but we also need to make sure that we destroy any descriptor set layouts, right? So that's obviously going to be the global descriptor set layout, right? And so we're basically just destroying these things in the opposite order that they were created, okay? And then of course, obviously the shader modules come last. All right. So the next thing that we're going to do is we are going to go ahead and set up a method to update what we're going to call the global state. And this is actually going to be responsible for loading all the data that we set on this object here, right? So we're going to set these at the very beginning of the frame, and then we'll call a method that will actually load all that stuff up. So if I go to Vulkan object shader H, right below use is actually where we're going to put this. We'll have a method called Vulkan object shader update global state. This is going to take the context, because we'll need that, and then obviously a pointer to the shader, okay? And I'm just going to take a copy of this, go back to the C file, and we'll fill it out down here. Okay, so thankfully this is actually pretty straightforward. So what we're going to do is first we're going to take some pointers to, first we're going to take a copy of the current image index so that we don't have to write this repeatedly. And then we're going to take the command buffer, which is basically going to be the graphics command buffers at image index, right? And we're going to take the handle of that. And then we're going to take the global descriptor at the current image index, right? So that we don't have to write all this verbose code repeatedly for all these function calls, okay? First thing we're going to do is we're going to bind the global descriptor set to be updated, right? And so we're going to do that with vk command bind descriptor sets. Now, you'll notice this is a command, so this is going to be run as part of a command buffer. It is going to be within the render pass. So we're going to say here, this is the command buffer that we're going to use. The bind point is the graphics pipeline bind point. Here is the pipeline layout that we're going to use. So after the layout, we have the first set, which is going to be 0 because we're just using that. How many sets we're going to be, descriptor sets we're going to be binding, that is going to be 1. The descriptor sets array itself, which is just going to be the address of the global descriptor here. The dynamic offset count and dynamic offsets are going to be 0. I'm not going to touch on those for right now. We will be using those later, but for right now I'm going to just pass over those. So that will bind our descriptor set. And the next thing that we need to do is we need to configure the descriptor for the given index. So we are going to define a range, which is basically just going to be the size of our global uniform object, and an offset, which for right now is going to be 0. That is going to be changing in the future, which is why I have them put here in variables. So the next thing is going to be, we are going to copy the data to the buffer. So here is where we take the data that is in the shader's global UBO, and we load it into the global uniform buffer, right? We use our offset, our range. That 0 there is the flags because we're not using any specific flags. And then of course, the data is the object itself, okay? So here's where we load that data up. And then loading the data to the buffer isn't quite enough. We actually have to then update the descriptor set saying, hey, the data in this has changed for this particular descriptor, so we actually need to go ahead and update that. So the first thing we're going to do is create something called a vk descriptor buffer info, which is going to give the descriptor update call that we're going to use information about the buffer, right? So it gives it the handle to the buffer as well as our offset and range that we created up here. Okay, and then here is where we are going to set up a structure about the descriptor set update itself. So we have here a vk write descriptor set, right? And we're just going to call this descriptor write. And this is actually what is going to contain the information to be written to the descriptor set, right? So we have our structure type write descriptor set. Our destination set is going to be our descriptor sets at image index, right? The destination binding is going to be 0 because it's the first one. The array element is going to be 0. The descriptor type, again, is going to be uniform buffer. We have one descriptor, so descriptor count is 1, and then the p buffer info is an array of those buffers. We only have one, so we're just going to pass the address of the buffer info to treat that as an array. And because that can take an array, technically you can update more than one descriptor set at a time, which eventually we will be doing. But for right now, we're only doing one, so you'll note that this says vk update descriptor sets, plural. However, we are only going to be updating one, and that is going to be our descriptor right here. We're going to pass the address of that because that expects an array. And then the last two are the descriptor copy count and descriptor copies, which we're not copying the descriptors for now, so those are 0. Okay, so that is all there is to updating the global state. It's not a heck of a lot of code, but there's a lot of concepts that have been covered here. All right, so now that we have all of this, we have everything we need in our shader to actually go ahead and use this information. So we need to expose some sort of way to update this global uniform object from the front end. Because right now we only have this Vulkan shader update global state available to actually do this. So we need to think about how to decouple this in a way where the rest of the application can send this data over and not really so much care about what shader, or even the fact that a shader is being used on the back end. And so if we go to Vulkan backend, between begin and end frame, we are actually going to want to do one more additional step. And that is, we are going to want to do something called updating the global state. And this is going to take a bunch of properties right now, and I'm actually going to build in some additional properties that we're not going to use right away, so that we don't have to keep changing this interface over and over again. But basically it's going to take the projection matrix, the view matrix, a view position, the ambient color, that's going to be the ambient color of the scene, and then something called a mode, which we will be using much later on. Okay? And so this is what we are going to use to actually set that data. Okay? So if we go back here to, so I'm just going to take this and go to end frame and put it right in between, right? And we'll fill this out here. So the very first thing that we're going to do is we are going to grab a pointer to the command buffer, and that is going to be in the context, graphics command buffers, and it's going to be context image index. Okay? And we're going to take the address of that, right? Oops, got those in there. Okay. So the next thing is, for whatever shader is currently bound, in this case, we're binding the shader here. However, I'm just going to make sure that we're using it again here, because eventually this temporary test code is going to be going away. I'm going to make sure that we use the shader first. And then we need our context object shader, right? Global UBO projection equals projection. Now, something to point out here. This is not passed as a pointer. None of these things are passed as a pointer because I actually do want a copy of these. Because when we pass this through to be processed and actually rendered, we don't want the rest of the engine to have to wait until this frame is done rendering to actually be able to update the state, right? To be able to move the camera, to resize the window, whatever. And so whenever we do this, we want this to be sort of immutable. Meaning once it's passed here, we can't change it. So we're taking copies of these objects instead of pointers to them to avoid that, right? So we're just copying the projection, and then we'll also do the same for the view. Okay? And then eventually other properties as well. So let's say to do other UBO properties. Okay? And once that's done, now we can actually call Vulkan object shader update global state. Now I do realize this right now does not support us switching shaders, and that's okay. As we expand on this architecture, we eventually will have the ability to bind to the proper shader as time goes on, but for right now we just need to keep things simple to get stuff up and running. Okay? And that is all there is to update the global state, right? We just pass these things in, we set them onto the UBO object here, and then we call this, which actually sets it in the shader itself. Okay? So now that we have this, we need to carry this up one more level and expose it to the front end so that the front end can then call this. However, we'll note also that our backend interface does not actually have a call to this. So if we look at our renderer types, we have our begin frame and our end frame for our background or our backend, but we do not have something available for the front end to call. So that is going to look like this. It's going to be the same function signature, and this is why I was saying I'm just going to create all of these now instead of having to change this a bunch of times. We're going to have to change this eventually anyways, but for now we have a function pointer to update global state, projection, view, position, ambient color, and mode. This also means that our renderer backend.c needs to have one more thing added to it. So right here between begin frame and end frame, we're going to set the update global state to Vulkan renderer update global state, right? And by proxy, that means that we will also zero this out on destruction. Okay, so that is, whoops, that should be renderer backend. Okay, so that is all we have to do to hook that up. So the front end is basically going to handle this within the renderer draw frame, right? So right here we have the begin frame, and then we have the end frame, okay? And so right here within begin frame, before we call end frame, we are going to call state pointer backend update global state, right? And for the projection and the view for right now, I'm actually just going to pass matrix for, oops, we don't have math. So let's include math. Let's go ahead and do kmath because we're going to need that. So we need mat for identity, right? We're just going to create and pass an identity matrix through every time for now. Same thing for view, right? So that's basically going to give us exactly what we have now. And then position, we're just going to call vec30 because we're not using that. For ambient color, we'll call vec4, call 1, we'll just pass white, right? And then for mode, we'll just pass 0. Okay, so all of these are sort of BS values for right now, and that's fine. We'll expand on these as we add cameras and so forth. But for right now, we just want to test that all of this works. Okay. So I believe this is actually everything that we need to do to hook this up. So let's go ahead and build. Let's see if we missed anything. It looks like we did. Vulkan types, unknown type global uniform object. So I probably forgot to include there. Yeah, so this is in renderer types, and I'll bet that's not included at the top. It is not. So include renderer types, I know. Let's build that again. Okay, it built. Let's go ahead and run. All right, and as you can see, we are getting all kinds of interesting errors here, but it does work. So what is going on here? Let's have a look at the logs. So looks like they're all pretty much the same and the same message. So we have here, let's just go to the bottom actually. We'll just work our way up. I suspect it's probably just one error, but okay, so VK command draw index none. Okay, type is object pipeline. Object 2, okay. Draw index defined with pipeline layout is not compatible for a maximum set statically used 0 with bound descriptor sets. Last bound with pipeline 0x0, so that apparently is null. The Vulkan spec states for each set n that is statically used by the VK pipeline bound to the pipeline bind point used by this command, a descriptor set must have been bound to n at the same pipeline bind point with a VK pipeline layout that is compatible for set n with the pipeline layout used to create the current VK pipeline as described, blah, 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 Okay, so what I'm thinking is this means that our pipeline didn't bind correctly. So actually, let me have a look here at the console.log and see what the very first error was. This might actually give us a little bit better of a hint. So descriptor set not bound. Here we go. So we're basically getting two errors repeated here. So descriptor set not bound. So we did not bind our descriptor set. All right. So let us have a look at our binding code, right? So let's go back to Vulkan object shader, and we'll do update global state. Oh, I'll bet I know what's happening. I will be willing to bet that it is because, or at least partially because, our backend is making these calls within start frame, which I knew this was going to come back and bite us. I just didn't think it was going to come back and bite us in this way. So I'm actually going to remove these from here. I'm going to cut these from here. And temporarily, I'm going to put them after the update global state call. Because basically these things can't be called before this, and I think that's partially at least what was happening. I don't think that's the full problem, but we'll see. Okay, let's go ahead and run again. All right, now we get access violation. So context. None of this is set, so is context null? It's not null. Let me build one more time. In fact, let me clean and build just to be sure. So that must have been it. I just needed to clean and rebuild after that one. So it was just an order of operations thing. We were binding everything correctly. If we look here at our log, everything is running as it should be. So there's no visual difference here, which is fine. That's something that we could go ahead and change. In fact, let's go ahead and change that now. Let me see how long this video has been running. Okay, so this video is going a little bit long, but I'm going to go ahead and change this up now, just for the sake of giving us something a little bit different to look at. So if I go back to our front end, let's go ahead and change the projection and view matrices, right? So I'm going to say mat for projection equals, say, mat for perspective. So we'll create a 3D camera here. We'll say deg to rad 45.0f. That'll give us a 45 degree FOV. Our aspect ratio, I'm just going to hard code this right now to 1280 divided by 720.0f to convert that to floating points. The near clipping plane, I'm going to say 0.1f. The far clipping plane, I'm going to say is 1000.0f. Okay, so that'll give us a projection matrix. Yes, I know we're recreating this every single frame. I realize none of this is efficient, and that is fine for now. We're just trying to get things up and running. So let's go ahead and let's see, projection is the first one, so let's swap that out. And then let's go ahead and also do mat for, we'll do mat for translation, and then we'll pass a vector3 position. So we'll say vec3, vec3, and then we'll pass 0, 0, and 1.0f. okay? And that is going to be mat4, and we'll call this view, right? So this is going to be our view matrix. And actually that might have to be negative, but we'll double check it. So we'll go ahead and plug view in here. And let me also make sure on the back end, oops, on the back end, when we're uploading our vertex data, we're using very small numbers here, which is not going to be very easy to see once we actually switch to a projection matrix. And I will explain the reasons why that is in a bit. But for now, I'm going to say const f32, and I'm going to blow those up by a factor of, let's do 10.0f. So we'll say, we'll just call it f, and then multiply all these things times f. Yes, I know 0. 0 times anything is 0, I understand that, but just to be consistent, I'm going to do that, okay? And so, let's see, we should have, oops, missing a semicolon there. So that should make the size of that a little bit bigger and easier to see. All right, so let's go ahead and build this and run. Okay, and yeah, that might have to be negative. So go to the front. I think that might have to be negative. Yep, okay. So obviously this square is very big now, but what we can do so what we'll do is we'll create a static f32z, and we'll set that to negative 1.0f, and we will feed in the z here, and then every time we call this, we'll just say z minus equals I don't know, 0.01f, right? So we'll just sort of hack change that over time so that we can actually see movement. Okay, and I'll move this up here and just watch, and you can see that that gets smaller and smaller as we move away. So, you know, if we can take a look at our, yeah, because this actually is not, this should be negative 0.5, and this should be 0.5. So that should be negative 0.5. So if we go ahead and run this, I'll grab this quickly. We can see that this properly is a square. It shrinks. Now obviously if we resize the window, it's going to screw up the aspect ratio because we hard coded it. But now that we've actually fixed these values here to actually be an actual square instead of a rectangle, it is in fact a square. So that is uniforms. I realize this is a long video, but I didn't really want to split this up into multiple videos, simply because I felt like all this stuff sort of belonged together. So anyways, guys, thank you so much for watching. I hope you are enjoying this series. I hope you learned from it. If you have any questions or comments, please drop them in the comments below. If you liked the video, please toss it a thumbs up. Go ahead and subscribe if you haven't already. Hit the little notification bell to get notifications as to when new videos in this or other series drops, and I will see you guys later.